So we have seen that block ciphers work on B-bit blocks. So this is generally 8 bytes or 16 bytes and so on. But generally we encrypt something larger than this because our messages are not that small. So question is, how do we encrypt big data? So easiest thing that comes to in our mind is shown in this picture, and this is actually known as the electronic codebook mode of operation. Every plain text block encrypt every plain text block independently, concatenate output blocks to form the ciphertext. So for instance, you have a 1 megabyte of file on your computer. So if you're using AES, you divide it into 16-byte blocks, and you independently encrypt each block with your secret key and obtain the ciphertext block. And at the end, you concatenate them in the same order and obtain the ciphertext. So your file is encrypted in this way. But although this sounds like a good idea, this is the worst thing you can do, and this will cause a lot of problems. The problem is that this mode of operation, ECB, maps same plain text blocks to same ciphertext blocks. So if P0 and P2 are the same, this means that C0 and C2 are the same. Attacker can capture information using this redundancy in the plaintext. So repetitions in the plaintext would cause repetitions in the ciphertext, and just by looking at this information, attacker can get some information about the plaintext. And easiest way to show is to encrypt a bitmap file. So let's look at our university logo. So this is a rectangle bitmap file. But there are a lot of repetitions in the data. As you can see, there are a lot of white pixels here. So if a single pixel contains 32-bit information, 4 pixels next to each other will provide you 128-bit data, which is just the block size. So each 4 bits would cause after encryption, would cause the same ciphertext block. So if you encrypt it with AES using the ECB mode, this is the ciphertext you would observe. So this is the original file. This is what you get after the encryption. So we are claiming that this is like currently the best algorithm we have, and the whole world uses this algorithm for encryption. But if you encrypt a BMP file like this, just by looking at the ciphertext, you can easily guess what the original file was. You can even read the name of the university here. So we have to overcome this problem. So BMP files are good examples why ECB fails in practice. This problem is not limited to BMP files. You can treat an encrypted file as if it is an image file and look at the pattern of the pixels to discover the type of the original file. For instance, executable files can be identified from the ciphertext because operations like memory accesses provide a distinct pattern in the image file, and so on and so forth. So this is not limited to BMP files. But ECB mode can be used for implementation, verification, or benchmarking to see how fast your implementation is. So ECB mode should never be used for cryptographic purposes. This is really important because we are still seeing in practice that people are using this. There are many applications or software you can download from the internet, and they are still using ECB, which is not a good idea. So NIST has a document, and in this 2001 version of NIST document 800-38A, they suggest the following mode of operations. The first one is ECB, but again, this is just for me, it is just for benchmarking. You should never use it. But the others are cipher block chaining, cipher feedback, output feedback, and counter modes. Then later on, they provided them extension to this document, and there they also added XTS because this is the full disk encryption standard by IEEE and also used by other organizations as full disk encryption standard. So which mode of operation you want to use, actually a choice. It depends on your actual concern about the performance and the security. And because some of them are parallelizable, and if you have more than a single core in your system, you might prefer something parallelizable and so on. So the first one was electronic codebook. This is how we do the encryption. And the encryption is as follows. The person who receives the ciphertext now has the ciphertext. they also have the secret key, perform the decryption operation, and obtain the plain text. But let's move on to cipher block chaining. So as you can see now, the encryptions are not independent. There are lines that are connecting this. So first you encrypt your initial block, but you XOR it with the initialization vector, which is something known that is specified in the standards. Then you perform the encryption operation and provide your first ciphertext block, but you also take it and XOR it to the next plaintext block. So this way, even if P0 and P2 are the same, now C0 will not be the same with C2. So this mode actually overcomes the problem of ECB, where you have this redundancy problem. But so this is a mode that is used in practice a lot, and the decryption works like this. Now the picture is reversed, but the problem is that now the algorithm is not parallelizable, because if you want to encrypt P2, then you need to know the previous ciphertext block. But in order to get this, you have to encrypt this, and in order to do that, you need to know this knowledge, and so on and so forth. So it is a serialized encryption. You cannot do it in a parallel mode. So there are some other modes which can be parallelizable. I'm moving on to the fifth one because this is a good example, and generally this is what I recommend. So instead of encrypting your plaintext block, just encrypt some counter. For instance, initially assume your counter is 1. So you fill your plaintext block with zeros and at the end a single 1. And you encrypt it with your secret key and obtain some information here. And then XOR it with your plaintext block and obtain the ciphertext block. Then increment your counter by 1. Do the same operation. Increment it by 1 again, and so on. So when you're communicating, you have to tell which counter you use, and they will also do the same operation here. So as you can see now, I don't say this is a decryption, but the person who wants to decrypt will do the same operation and obtain the same value here like you do. But what you did was to XOR your output with your plaintext block and obtain the ciphertext block. But the person who wants to decrypt the message now has the ciphertext block, so they XOR it with this output and obtain the plaintext block. This works in this way because XOR operation is just modular addition, addition in modulo 2, so this is how you can do it. So encryption and decryption is almost the same. You only switch the places of ciphertext and plaintext. So this is really good because, as you can see, there are not connecting lines between these encryption operations. So this means that it is fully parallelizable. If you want to encrypt this plaintext block, you can just know the counter and do it. So, or if you want to decrypt some part of the ciphertext, you can just do it here, and you don't need to do the rest. So this is actually what, for instance, iPhones come with. Their default choice is the full disk encryption, and this is they are using actually this mode of operation, and instead of counter, they are just using the block number where they're writing the data on the hard drive. So important thing is that you need to change your counter when you're encrypting a different file or encrypting something else. Using the same counter for different encryption operations would provide the same output here. We generally report it as key stream. So this would cause a problem. An example is as follows. Initial Turkish version of Cryptology, which was a famous ransomware, used AES in the counter mode. And what they did was to encrypt first 2 megabytes of your files, keep the rest the same, but since you lose the first 2 megabytes of your file, you cannot decrypt them. So a ransomware works like this. By probably clicking a link in an email, you actually allow a malware to be downloaded into your system. It encrypts a lot of your files, most on your desktop and some important folders, and then they ask you to pay some Bitcoin. And at that time, they asked for 2 Bitcoins, but at the time, it was like $600, but today Bitcoin is around $18,000. So they ask for 0.0 something Bitcoins from you, and if you do it, they will decrypt your files. But as I told you, they use the same counter for every file encryption. So this means that obtaining one unencrypted file, so like this. So assume that you have the ciphertext here, because they encrypted your files. But if it is a file that you can also obtain the original version, like if it's a PDF file that is also on the web, you can download it and you can also get the plain text blocks. So if you XOR your ciphertext with your plain text, you will get the values here, which I called key string. So if you know this, and since they use the same counter for encryption of every file, now for a file, another encrypted file, just you know these values, just XOR with the file, and you get the plain text. So this way we actually rescued a lot of files of a lot of people, but after that they also noticed this problem and updated the ransomware. So if it is implemented in a good way, actually there is nothing you can do to recover your files. So let's finish our lecture by returning to our example. So we started with the encryption of a BMP file in the ECB mode. We said that it is like this, but I said that if you use something better like CBC or counter mode, you will be more secure. So this is what would happen if you had used counter mode. As you can see, there are no significant patterns anywhere. So it is like a complete noise to you. So this is the original picture. This is ECB encryption, and this is counter mode encryption. So it doesn't matter which encryption algorithm you are using. Actually, which mode of operation you are using is also that important. So if you people who doesn't know much crypto actually uses ECB, and as you can see, it doesn't provide you any security. You have to choose your mode of operation that is known as a secure mode of operation.